Hello, everybody, and thank you for the invitation to present today some of the research I have been doing. My name is Reyes Garcia. I'm Associate Professor in Structural Engineering at the University of Warwick in the UK. And today I'm going to talk about the use of recycled aggregate concrete in structural components, and I will show you some of the recent research we have been doing. I'm also visiting professor at Walilac University in Thailand, and that's relevant because much of the material I'm going to show you today is actually coming from the collaborations I have with Walilac. So I hope you enjoy the presentation. These are the contents of the presentation. First, I'm going to introduce a bit of the background on construction and demolition waste. Then, obviously, we have to ask ourselves, why do we want to use recycled aggregate concrete in new concrete? And then we're going to spend some time looking at the recent research work we have been doing to eventually reach the conclusions and the main takeaways from this presentation. So I suppose the first question we have to ask ourselves is, why do we want to use waste in concrete? And to answer that, we have to think about how we use or how we abuse concrete in the world. If you think about it, concrete is the most used material in the world after water. And for every one of you watching this presentation, there will be at least 3 or 4 tons of concrete cast per year. So we're talking about a lot of concrete every year. And that's going to be the trend. As our countries develop, we will carry on demanding more concrete for new structures. Now, in that regard, the construction industry is a top user of raw materials. We can see here in this plot, these are basically the trends in the last few years of the demands of aggregates to produce new concrete. That's basically the sand and the gravel we use for the concrete. And as we can see in this figure, most of the demand comes actually from Asia. China, India, and Southeast Asia are the countries that are demanding more aggregates to produce new concrete. Now, we also have another issue in construction, which is as our countries develop, many times we have to renovate big parts of our cities. So we demolish those structures built in the 20s, 30s, 40s, and 50s in the last century. And we're basically building new buildings, high-rise building, most of them. And as a result, we have continuous streams of what we call construction and demolition waste that we need to try and reutilize as much as we can in construction itself. So we have 2 things here. One is obviously the demand for new aggregates, of new materials to produce new concrete. And on the other hand, we also have a continuous stream of construction and demolition waste that we need to try and use as much as we can in construction. Another fair question would be, why do we want to use what we call recycled concrete aggregates in new concrete? And to answer that, we can look at this table that is basically showing the main constituents in construction and demolition waste. And if you look at the table, actually most of the construction and demolition waste is actually made out of concrete and masonry. Those are basically these 3 figures here. You can see that those components are anything between 8 up to 84% of the construction and demolition waste. So actually most of that waste is actually made out of concrete or masonry. And as a result, if we recycle concrete and we know how to use it, we can recycle it as aggregates to produce new concrete. Now, we want to replace natural aggregates with this recycled concrete aggregate, basically because if we think of a normal mix, this is what we have here on the right, in a typical mix, around 60 to 70% of that mix is going to be aggregates. That's basically the sand and the gravel. So that's what we're trying to replace by using the recycled aggregates. Now, the use of recycled concrete aggregates, or simply RCA, has several technological and scientific challenges because it's a family of materials. So we need to understand and characterize RCA so that we know how it's going to work in the final concrete. And this is some of the things I'm showing in this slide. There are different challenges with the use of both the recycled aggregate, RCA, and with the final product we get, which is the recycled aggregate concrete, which I will call simply RAC. Now, RCA, that's the aggregate itself, is more porous and it's also weaker than the normal aggregates we use in concrete. And this is for different reasons. I'm going to touch only on two. One of them is the adhere mortar, because this is basically recycled material from an old concrete. So there is always some mortar attached to the little bits of aggregate we get. And that increases the porosity. And therefore that absorbs more water when it comes to the mix and the mix design. The other issue we have with RCA is the way we recycle RCA. Many of the times, what we do is we do mechanical recycling. So basically, we crush the old concrete to produce the chips and the new gravel for the RCA, and that creates cracks and it creates also damage in the gravel and in the little pieces of new aggregate. And as a result, we need to understand and characterize RCA properly to know its properties and to know how to utilize it properly to produce a new rack. Now, as a result of those issues, that RCA is more porous and it's also weaker, that is going to lead to a lower strength concrete than what we usually have with natural aggregates, especially when we try to replace high volumes of aggregate. Just to give you an idea of the issues we have, here on the left, we have water absorption of normal aggregate versus recycled concrete aggregate. And this is absorption on the vertical axis. Then we have results from different researchers that have looked into it in previous years. On the left, we have the normal aggregate. And then we have on the right of these columns, the recycled concrete aggregate. And as you can see, all the columns, all the orange columns, which is the recycled aggregate, have a higher water absorption. Yeah, so that's going to affect the fresh properties of our rack. And then, speaking of rack, this is now the concrete. This is the aggregates. This is the concrete. In terms of strength, as we increase the amount of replacement, the amount of RCA we use in the mix, that's going to reduce the strength. So in the vertical axis, we have compressive strength. And then again, for different researchers that have looked into that in previous years. And we can see in the case of normal aggregate, which is what we call NAC here, that's the baseline, that's the comparison. All of them have a certain strength. In the case of rack concrete with recycled aggregates, we always get a lower strength. Yeah, so that's an issue we need to try and solve. Now, with my collaborations with One Lilac, what we have been trying to do is basically produce our own recycled concrete aggregates. And to do so, we started by designing our own machine. I don't have the time to show you how it operates, but it's basically inspired by what people do in the plastic industry. So this is the machine, and we basically feed the machine here from the top with concrete cylinders or cubes, whatever it is. And then there are a series of jaws there that crush the concrete. And then at the bottom, we have several sieves that give different sizes of aggregates. So we have this little machine that basically helps us with our research and with the projects we have in Thailand. This is a view of the sort of recycled aggregate we get from the little machine I showed you in the previous slide. We can produce different sizes from all basically 0 millimeters up to around 24, 25 millimeters. So we can cover all the ranges of recycled concrete aggregates. And this is a view of how it looks in bulk. Now, replacing part of your aggregate with RCA is not a big issue if you replace small volumes. So let's say up to 20% of level of replacement, it's okay. If you look at the ACI 318, the American code actually allows you to replace some of that aggregate with RCA, and you can still use the same equations to do your calculations, to calculate your beams, columns, and so on. So there is no big issue if you replace only a fraction, around 20-25% of your aggregate with RCA. Now, when you increase the amount of replacement, let's say to 50%, that's when the problems start, because you can get anything. Sometimes you don't reduce the strength, but sometimes you do. So it's a bit of a gray area there. And obviously the problem comes when you increase to the maximum potential of aggregate. If you replace completely your natural aggregates with recycled aggregates, that's when we have serious problems, not only with the workability of the fresh mix, but also with the strength, because the strength drops dramatically. And in general, there is limited research and limited knowledge of what happens with that recycled aggregate concrete, with that rack. And therefore the question is, if we are replacing very large amounts of RCA, of our aggregates, and that reduces the strength, what can we do to recover some of the strength and actually use that rack in structural applications? And to basically answer that question, what we have been doing is to use passive and active confinement around rack elements to see how much we can increase the strength. And to understand a bit of what can actually confinement do for us, we need to go back to the basics and understand how confinement can increase the strength and the formability of concrete. And that's basically what I have in this slide. In this slide, if we look at it, we have here on the left, this is a small concrete cylinder. That is usually what we get to test to know the concrete strength. And if you look at this plot, we have a series of loading platens here at the top and bottom. Then we put the cylinder in the middle, we compress it, and we get the strength, the compressive strength of that cylinder. That creates a complex state of stresses here within the cylinder. But at the end of the day, what we want to get is the stress, which is basically what I have in this plot in the vertical axis. We have the stress or the strength of the concrete versus the strain. On the right hand side, I have the vertical strain. That's how much the cylinder deforms in the vertical direction, and this is what we used in design. And then on the left, on this side, I have the lateral expansion, the lateral deformation of a cylinder. And then basically what we want to do with this confinement is to change this behavior, this stress strain behavior, which if you look at it in this plot, it could be something like this. With the confinement, we want to change it to something like this. We want to increase both the strength in the vertical axis, but also the deformability of that concrete in the actual direction by controlling the lateral expansion of that concrete. Now, there are two types in general of confinement. One is called passive and the other one is active. What I'm showing here is passive confinement. That's the confinement we usually give with hoops or with stirrups. But we also have active confinement. And the main difference is when you activate that confinement. For the case of passive confinement, which is this one here, this basically block here, passive confinement only activates when your cylinder is actually cracked. So you need a certain level of damage in your cylinder, some cracks there, to activate the confinement. With the active confinement, on the other hand, we can actually apply some pre-stressing on the confinement and activate it much before that, even before the concrete cracks. One of the techniques we can use to apply active confinement, this is basically coming from my PhD studies. One of the things we can do is to apply what I call post-tension metal strapping. And that's essentially using strapping tools and metal bands, like the ones used for packaging, boxes in the packaging industry, to apply bands around concrete. And that's basically what's shown in this video. If you see, the method is relatively simple. We take the metal straps, we put them around the concrete like sort of belt, and then we have the metal clips, because we apply tensioning force on the metal straps. With the clips, we secure that force in such a way that we confine actively that concrete. And if you think about it, the principle is very simple. It's more or less what weightlifters do. A weightlifter, to take more weight, they basically belt up themselves. Here you can carry on watching the video, just to give you an idea of what the metal strapping can actually do in terms of increasing the strength and the formability of concrete. I have this plot here. On the vertical axis is basically concrete strength, the compressive strength of different cylinders shown here. And on the horizontal is the actual strain of the cylinders. And then we have different cases. This one here that says control is basically a normal cylinder without any PTMS strapping. And as you can see, it reaches around 30 megapascals, and then the response drops to this level of strains. Now, the last cylinder here that says S prime equals 0, it's basically this cylinder here. So it's a fully confined cylinder with the metal straps. And as you can see, the metal straps increase the strength to around 46 megapascals, but also importantly, it increases the strain, the formability of that concrete. And during my PhD, I had the chance of doing several tests on lap spliced elements, beam column joints. I had also the privilege of testing a full-scale building in the CSI Clay laboratory in France. But again, all of this is basically on normal concrete. So what we decided to do with my colleagues at Walailak University in Thailand is to use the technique I had developed in my PhD and apply it now to rack cylinders to see how much we could actually increase the strength of the rack, to see how much the metal straps can help us to recover some of that strength that we lost by using recycled concrete aggregate. I don't have the time to go through all the details, but I'll focus just on the main results. For instance, this plot here, what we have on the vertical axis is the normalized strength. So that's basically how much we are increasing the strength over the control specimens, which is basically a specimen, a cylinder without any metal straps around. And then the other four columns here correspond to these specimens here with different spacings of the strap, because that's one of the variables you can control, and a number of layers. In particular, for these two last cases, this one is only one layer of metal straps, and this one is two layers of metal straps, one on top of the other. And as expected, for this last case, the increases were excellent. We increased the strength, the compressive strength, by almost 200% to get a strength of around 60 megapascals, which is clearly a concrete we can use for structural purposes. In this particular piece of research that we published recently, we also proposed a new stress strain constitutive model for this type of concrete, which is rack concrete confined with the metal straps. And this is basically shown here in this plot at the bottom. Now, we did some of that research on the cylinders to have a preliminary look at the behavior of rack confined with the metal straps. But of course, we know those are not real columns. So what we did is we basically scaled it up and we built up slightly larger elements. And also because we were interested in assessing the effect of slenderness in the effectiveness of the metal straps, what we did is produce this setup, which I'm showing here. And if you see the setup here at the bottom, this is the column, this is the column element. There is a hinge here at the bottom, and then here at the top you can see the load, which we started applying eccentrically. So we had specimens where the load was perfectly at the center of the column, but then we started shifting that load to produce some eccentricity and see the effect of the eccentricity in the response of the columns. Just to give you an idea of what happened in this plot here, I have the axial stress, that's basically the strength of the columns we tested. And then here on the horizontal axis, we have the axial strains, and then we have different cases. This is basically a non-confined column, so no metal straps around the column, so it had this behavior. And then we had two different spacings of the straps in this particular set of tests. One of them with a spacing of around 50 something millimeters, which is basically leaving a gap of 25 mil between them, and then another one at around 25 millimeters. And as expected, the closer the straps are, the more the effectiveness of the system, and therefore the better the response. You can see here that the strength increased from around 20 something megapascals to around 38 megapascals. Obviously, we did also some numeric analysis. You can check the results of this research in the Journal of Structural Concrete. We did some numerical analysis to try and predict the behavior of the columns, and then do some more parametric analysis to establish the effect of the slenderness. And something we found is, as expected, as we increase the slenderness and the level of eccentricity of the load, the effectiveness of the metal straps reduces a bit, because obviously it's not only the confinement that comes into play in the response, but also the eccentricity and of the load and the slenderness of the element. But all in all, the metal strapping was effective at increasing the strength of the column, and by increasing the strength and the deformability of that concrete, the behavior of the columns was improved significantly. These are some of the tests we are doing at the moment at Walilac with my colleagues in Thailand. And in these tests, what we are interested in is exploring recycled aggregate concrete beam column joints confined with metal straps. So if you think of a building, this is a building, a frame building, we can extract a part of that building. These dots here are essentially the points where we idealized a zero moment point. So we can extract part of this building. Then if we sort of ignore the stubborn beams at the sides of that beam column joint, we end up with a sort of T element that we can test more or less easily in our laboratories. And that's basically the element you see here tested in this frame. In this case, due to the headroom of the frames they have in Thailand, they can only test it horizontally. So in this case, this is the column, what you see here laying horizontally, and this is the beam. We have done some numerical analysis because obviously we need to know in advance what's going to happen with those rack joints. And what we will try to do is to do something similar to what I did for my PhD, which is test some joints with a grid of post-tension metal straps placed in orthogonal directions. And then at some point we will also try to do some strapping in the diagonal directions. I think one of the most promising applications for rack is actually to use rack in composite slabs. And this is for different reasons, but one of the main ones is that usually the problems in slabs are not related to the strength, to the resistance of the concrete, but rather to serviceability. And most of the times the requirements in terms of strength in slabs are not as severe as in other elements like columns or beams or even beam column joints. So what we did is basically try to use rack in these slabs, and we tested in different conditions to find out the ultimate resistance, but also serviceability, which is one of the main issues in these slabs. These are just some of the results. We tried to do short-term and long-term loading in terms of the, here we have the load versus the deflection, comparing normal aggregate concrete slabs to rack slabs. In that sense, yes, there is a difference. The behavior of rack slabs is slightly lower, slightly less effective in that sense at controlling vibrations and deflections, but it's not as bad as we thought initially. We also did some vibration tests trying to induce some human vibration on those slabs. We used a treadmill, and then we asked participants to basically walk, run, and jump on that treadmill to measure the vibrations and the accelerations in those slabs. And what we found is that, again, in general, yes, because rack has a lower elastic modulus in the concrete, we observed higher vibrations, but in all the conditions we examined, the levels of vibration and acceleration actually remained within the limits that we have in the current codes. So in that sense, we were confident that we could use rack in composite slabs as well. We also did some fire tests on similar slabs to the ones I showed you in the previous slides, with and without openings, to basically see if the fire made a difference in terms of the behavior compared to normal aggregate concrete slabs and the rack slabs. And the answer is yes, we observed a different behavior. But again, in terms of general fire behavior, even when the fire affected the behavior, especially at the debonding area between the metal deck and the slab, because obviously the rack is a bit weaker, we observed a bit of separation there, slippage between the two elements, but the difference is not massive. So yes, we can use rack more or less confidently for composite slabs, even if these are subjected to fire. This is an interesting project because basically in Southeast Asia they eat lots of pork, and we had this interesting project with a farm. Basically the issue here was the durability of the slabs they had on the floors, because basically what happens is you have the pigs there. Obviously the wee and the poo needs to be washed away. Everything comes to these slatted slabs here in the middle of this compound where they keep the pigs, and everything drains through these slatted slabs. Now the issue is obviously the durability of those slabs is very, very short. A, because they are made with normal steel reinforcement, and B, because the concrete there is not explicitly tailored to sustain that level of demand coming from the pee and the poo from the pigs. So they reached out to us, and what we did is we tried to help them, and we designed this series of hopefully more durable slabs made of rack. And rather than using normal steel reinforcement, what we did is we use fiber reinforced polymers, so basically bars made of glass FRP inside, to examine for how long those slatted slabs are going to be there. But there is no doubt durability is an area that requires more research, particularly examining the long-term behavior of rack structures. Okay, this is my last slide. So a few conclusions and the main takeaways from this presentation. I think it's undeniable that there is a huge potential for the use of recycled concrete aggregates, the little gravel and the little sand in construction. And obviously, this is very much pushed by the need of adopting circular economy approaches in construction. I think in particularly in developing countries in Asia, Southeast Asia, and so on, that's going to be especially the case because in the foreseeable future, we are going to carry on renovating our large urban centers. Now, we can actually use the recycled concrete aggregates in recycled aggregate concrete. That's the new concrete we're producing for different structural applications. The ones we are examining at the moment are columns, beams. I didn't show you much on beams, but we also did beams, and particularly slabs. I think slabs are, we basically can use them as they are now. But of course, we need to keep in mind that concrete is not a material, it's a big family of materials. And therefore, we need to understand and characterize the recycled concrete aggregate before we use it. So we need to know how much water it absorbs, abrasion, density, and so on, so that we can know the effects both on the fresh and the hardened properties of the new rack. We can always strengthen recycled aggregate concrete. We can use the metal straps. We also did some work with internal steel fibers, but obviously we have to keep in mind that that may actually increase the cost of the concrete. And when it comes to construction, cost effectiveness is one of the main things to keep in mind. So we need to make our solutions as cost effective as possible so that they are competitive in the construction market. And as I mentioned in my last slide, the long-term behavior, durability, the behavior of rack elements in harsh environments is something that we still need to look into. And finally, probably the main takeaway as civil and structural engineers, we need to understand properly how the recycled concrete aggregate affects both the fresh and hardened properties of the final rack products, whether these are columns, beams, and so on. And therefore, we need more research because basically we know how to design with normal concrete. So you can actually modify those equations, those guidelines we have in the codes to design now recycled aggregate concrete elements. And with that, I conclude my presentation. I thank you for your attention. My special thanks also to Dr. Tanongsak Imjai and all the research staff at Walilac University in Thailand. I'm happy to receive any questions, comments, or who knows, even collaboration opportunities from you if you think I can help you in some way. Thank you very much. I hope you enjoyed the presentation. Thank you.